will wait for a few minutes. Let's see if other students also join, and then we can start today's problem solving session. So just to be clear, am I audible? Okay. Okay, we'll wait for say 2 more minutes to see if other students join, or else we will start the session. Okay. So, by the way, we are in the week 3 of the Thermodynamics course taken by Professor Anand from IIT Palakkad, and in this week we will be primarily dealing with heat transfer and problems related to it. And there's so I will briefly go through the concepts that were taught by Professor Anand in the lectures. Just briefly go through it. I will not dive deep to all the topics and then we'll solve one of the questions that were taken by Professor Anand in the lectures, so that we can just revise our concepts and implement it in the problem that we are solving. And then finally I will solve some few problems that will help you to solve the questions for this week's assignments. Okay, so I guess that's all. I guess we can start today's session. So welcome back to the week 3 of the problem solving session for the for the thermodynamics course. So as we already discussed, thermodynamics is a science that deals with energy and its conversion and transformation. Okay, and this energy conversion is or modes of this energy transfer is achieved by two ways. Okay, that is first through heat transfer or work transfer. So work transfer we have dealt with in the previous week. So this week our agenda is to deal with discuss the heat transfer. Okay, so heat is an interaction between a system and surrounding which occurs solely by the virtue of temperature difference between the two. Okay, so if two bodies have temperature differences between them, so there is bound to have a heat transfer between them. Okay, so and this spontaneous heat transfer occurs between a system and a surrounding at when there is a difference between the temperature of the system and the surroundings. Okay, and the direction of this spontaneous heat transfer is from higher temperature to lower temperature. Okay, see, I am not saying that heat transfer cannot occur from lower temperature to higher temperature. Of course it can occur, but for that we have to use some external forces or external ways, or we have to input some external energy to do so. Okay, example is heater or air conditioner. Okay, so in that case, in the case of heater, we heat the warmer region, and in air cooler we are forcibly cooling a zone to a lower temperature. Okay, so that's the case. But in nature, or in nature, the heat transfer where the spontaneous heat transfer occurs, like or in nature where the heat transfer occurs spontaneously, that is like heat transfer occurs by itself. For that heat transfer to occur, the heat flux direction of heat flux is from the higher temperature to lower temperature. Okay, only in the case of spontaneous heat transfer. I'm not saying only, but spontaneous heat transfer could occurs from higher temperature to lower temperature. Okay, and of course the vice versa is also possible, but that it will not be termed as spontaneous. Okay, and again, as I discussed in the previous week, that heat transfer is a path function and it's not a property of the system. Okay, so heat transfer, similar to the work transfer, depends on the path followed by the system to achieve it, or to absorb heat or release it. Okay, so heat transfer is a path function. That's why we denote heat transfer again as a inexact differential. So we use a denotation of delta. Okay, not a direct differential, we do not denote heat transfer as dq, rather we denote it as delta q. Okay, because it's an inexact differential. And the units of heat transfer is again same as work, so the units are joule and calories. Okay, kilocalories or kilocalories you can use by anyone, but for the SI units, the units for heat transfer is joule. Okay, now this is the important part, that is the sign convention. Okay, so as I discussed in the previous week, for a work transfer, if the work transfer is from if the work transfer is into the system, then it is negative, and if the work transfer is from the system, or basically the work is done by the system, then it is positive, right? So work done by the system is positive and work done on the system is negative. In a similar fashion, the heat induction also follows a general convention that is followed in most of the textbooks. So that is, if heat is transferred into the system, then it is taken to be positive, and if the heat is transferred away from the system, or heat is given from the system, then it is termed as negative. Okay. So as I mentioned last week also, this convention is something that has been followed in most of the standard textbooks and research papers. So that's why I am also Professor Anand is following it, and similarly I also like to follow this convention only. But of course, the vice versa is also possible, but then like you have to change everything accordingly. Okay, you have to mention it, but just for the safe side, or just for the ease, or for our convenience, I would prefer, or I will request that you can follow this sign convention, because it is through this sign convention only we are defining or implementing the first law, second law, and third law of thermodynamics. So all the thermodynamic laws that we will read in this course will follow this sign convention. Okay, so I don't want to repeat it. It's a trivial thing, but it's important to remember. Okay, just as an introductory course to thermodynamics, the sign convention is very important to remember. So the zeroth law of so then we discuss the zeroth law of thermodynamics. So the zeroth law of thermodynamics states that if a system A is in equilibrium with a system C, and system B is also in equilibrium with system C, then both A and B must be in equilibrium with each other. Okay, and this zeroth law of thermodynamics is implemented primarily in the principle of thermometry, and Professor Anand might have discussed a lot of examples of different types of thermometers. There are liquid in glass thermometers, then there are ideal gas thermometers, then so he discussed different types of thermometers. Okay, so again I'm not going to go through the entire derivations, but I'll just go through one or two formulas because we will be using it in today's session. So I'll just go through it. So in the case of a liquid in glass thermometer, we express the column length as a suitable function of the temperature. Okay, column length, basically if we are using mercury as a fluid to denote the temperature rise or to measure temperature, then this rise in the length of the liquid column of mercury is denoted as a function as a simple linear function of temperature. Okay, so L is the length of the liquid column, A and B are constants, and T is the temperature that we are measuring. Okay, and for the purpose of calibration, we could use the known temperatures such as the ice point, that is 0 degrees Celsius, and the steam point of 100 degrees Celsius. Okay, so this linear relation needs to be calibrated. By calibration I basically mean we need to determine the value of these constants A and B, right? Because different materials, different liquids will be calibrated accordingly, and thus will have different values of the constants A and B. Okay, that's why we need to calibrate it by using a known temperature that we know for very fact that at when the liquid is at the ice point, or when the liquid freezes or water freezes, it is at 0 degrees Celsius, and similarly when the water boils, it is at 100 degrees Celsius. So we know these temperatures for sure. So using these values we can solve the two equations that we get from this linear relation, and then find the value of the both constants A and B. Okay, so there's something that we'll do today also in one of the problems that we'll solve. So you can recall it and try to solve it using this understanding. Okay, so this, if we know the value of temperatures at value of the length at two different temperatures, then we can Substitute the value of these temperatures for T in this equation, then we will get two different equations. Say L1 is equal to A plus BT1 and L2 is equal to A plus BT2. Then solve these two equations, get the value of A and B, and then you will get a linear relation between A and B. Okay, a linear relation between a linear relation between L and T. Okay, once you know the value of the constants A and B. I hope it is clear, like how we calibrate the temperatures, and by knowing the length of the liquid column of thermometers at two known temperatures. I hope it is clear. You can just write yes, no, or just say yes or no. Okay, then I hope it was clear in the lecture itself. So I'm just repeating it just for quick revision. Okay. Then there is the ideal gas thermometer. So there are two different modes. That is the constant volume mode or in constant pressure mode. Okay. So in the constant volume mode, the volume of the gas remains, the volume of the volume of the system that we are considering remains constant, and the pressure varies linearly with temperature. Okay. Similarly, in the constant pressure mode, the volume varies linearly with the temperature, and pressure remains constant. Okay. So again, I'm just not going to again go through it entirely, just as a quick revision. Okay. Also this. Okay. I'm sorry. Okay. So now we'll discuss the modes of heat transfer. Okay. See, I'm sorry. Uh, in the subject in the in the mechanical engineering course, so we have a separate course or separate subject for heat transfer. Okay, where there is a detailed understanding and analysis of the three distinct mode of heat transfer, that is conduction, convection, and radiation. Okay, but just as an introduction, but for the scope of this course, that is thermodynamics, we will just go through very briefly about these three modes of heat transfer. We will see the governing equations of conduction, convection, and radiation. And for our assignments, we will solve some problems related to it. So that's all we will discuss. But you need to know that this heat transfer has a completely different subject of its own. Okay, so it's a very deep and vast subject, and can be studied as a separate course if needed. Okay, so and for the scope of this course, our course is thermodynamics, we are just giving a very brief overview of these three modes of heat transfer. Okay, just to know that, just for you to know about these modes of heat transfer. Okay, so for conduction, the governing equation that uh, the governing equation for conduction is the Fourier's law of heat conduction. Okay, so this is given by the net heat transfer. The net rate of heat transfer is equal to minus Ka delta T by delta X. Okay, where delta T is the net temperature difference between the 2 points, and delta X is the difference between those two lines. Okay, so I'll just use a diagram to make you understand. So if say we are trying to find the rate of heat transfer across a slab of a slab of brick, say, then if if you are trying to measure the temperature between net heat flux between these 2 points, then say that the outer surface or the left surface of the slab is at temperature T1, and the right surface is a temperature of T2, and T1 is say greater than T2, then then the spontaneous heat transfer that I mentioned previously would occur from direction of T1 to T2, or basically it will be in this direction. Okay, from left to right. Now from the Fourier's law of heat conduction, the net rate of heat transfer Q dot is given by minus K, that is the thermal conductivity. K is the thermal conductivity. A is the area of this slab, or area through which we want to measure the net heat transfer. Then it will be the planar area of this brick. So if you consider a 3D projection of this brick, then then it will be something like this, right? this will be the area, okay, A, okay, the area is constant in this case, so that will be the area, and delta T by delta X, so it will basically be the temperature difference between the 2 points, so say it is T2 minus T1, and the length, so say the length is L, then it will be L, so this will be net rate of heat transfer across this wall of length L having a temperature difference of T1 minus T2 or T2 minus T1, okay. So the minus sign is just basically to make this net of rate of heat transfer to be positive, because see, since T2 is less than T1, then this difference will be again negative, so this will be negative, then the product of two negatives will give us a net positive rate of heat transfer. So it basically means that the heat transfer is in the direction of the direction that we chose beforehand, right? So we are saying that the heat transfer is occurring from left to right. So if the net heat transfer turns out to have a positive sign, then the chosen direction of heat transfer is correct, okay. So if at all, if in some way it comes out to be negative, it will basically mean that the direction of heat transfer is in the opposite direction. So instead of going from the heat transfer occurring from a higher temperature to lower temperature, in this case it is occurring from, if it turns out to be negative, then it is occurring from right to left, okay. So heat is coming out of the wall towards the outward direction, okay. So that is what it will basically mean, okay. So now again Professor Anand very beautifully gives a range of different thermal conductivities for different materials. So in the case of metals, the value of thermal conductivity is in the range of 100 watt per meter Kelvin, okay. So the unit of thermal conductivity K is watt per meter Kelvin, okay. So do not confuse K with this K. So usually this is denoted as sometimes as kappa, but so this is denoted as kappa, okay. But thus for the sake of writing, I am not able to distinguish it properly, but you need to know this is denoted as kappa, okay. And the unit of thermal conductivity is watt per meter Kelvin. Then for metals, the range of thermal conductivity is in the order of 100, okay. Metals have very high thermal conductivity. Similarly, in the case of non-metals, they will have a range from 1 to 10 watt per meter Kelvin. For liquids, it will have a range of 0.1 to 10 watt meter per Kelvin. And in the case of insulators, it will have a range of 0.1 watt per meter Kelvin. In the case of gases, it will be in the range of 0 to 0.01 watt per meter Kelvin, okay. Why this is important? Because there is one question in this week's assignment asking match the following question, right? Asking you to match the materials with their respective thermal conductivities. So if you know at least even know the range of thermal conductivities that the particular metal lies within, then you will be able to correctly match the thermal conductivity. So because you will clearly see that the given thermal conductivities are in a particular order of magnitude, say in tens, hundreds, or in ones or 0.1. So this order of magnitude of the thermal conductivities are distinct, so distinctly given, so you will be able to match them accordingly if you know the order of thermal conductivities of these materials, okay. That's why I was just discussing it briefly, so you can solve the assignment problem. So this is what I basically discussed just before, so that's fine, okay. Now we discuss the convective heat transfer, okay. So in this case again, this mode of heat transfer is primarily because of the bulk flow of the media. So in the case of conduction, it was basically because of diffusion. So like if we apply heat to a particular surface, the atoms of the surface start oscillating, which results in the rise in temperature of the material, okay. So this, in the case of conduction, the heat the way through which the objects get heated was through diffusion, okay. But in the case of convective heat transfer, this heat transfer basically occurs because of the bulk flow of the media, okay. So in the case of flow of say liquids and gases, if the bulk flow of these liquids and gases results in the net rate of heat transfer. Okay, but by no means I'm saying that convection won't have conduction. Of course, conduction needs to be there in the case of convection. It's a convection also, but the majority of the heat transfer that occurs in the case of convection is because of the bulk motion of the medium. Okay, we will see when if you are at all going to take the heat transfer course, you will see that when we are dealing with convection, you will have to deal with convection. So you will, sorry, when you are dealing with convection, you will have to deal with conduction. Okay, because it is through that only the heat transfer occurs through the say I will give you one example. So if in a particular heat transfer question, if you are asked that there is a wall and air is flowing outside the wall, because of which it has some certain value of convective heat transfer coefficient. Okay, and the room is at room is at temperature T1, the outer surface of the wall is at temperature T2, and the air that flows above the wall along the wall is at a temperature T infinity. Then the net rate of heat transfer because of convection between T2 and T infinity you can find through this formula, right? But the problem is complete when you are able to find the the total temperature at the net temperature at the inside of the wall is at T1, right? To find this T1, you need to find the net rate of heat transfer across T2 and across this wall because of temperature difference of T2 and T1, and this you can only find when you apply the concept of the Fourier's law of heat conduction. Okay, so all the convective problems will definitely have the conduction element also, but just to make sure that the majority of the heat transfer occurs because of the this uh, flow of air or flow of any fluids across the or above the wall of the or above the surface of the wall. Okay, so because you will see that the net rate of heat transfer is primarily because of this. Okay, basically, like, you will see a vast temperature difference between T infinity and T2 and very slight temperature difference between T1 and T2, which says that the majority of the heat transfer has occurred because of the convection. Okay, now again, so here also the convective heat transfer coefficient will have a different ranges. For in the case of natural convection, the convective heat transfer coefficient varies from 5 to 25 for gases and 5 to 100 for liquids. Okay, in the case of forced convection, this convective heat transfer coefficient varies from 25 to 250 for gases and 50 to 20,000 for liquids. And similarly, in the case of boiling phase change, this convective heat transfer coefficient varies from 2500 to around 1 lakh. Okay, so we'll clearly see that by natural convection we mean that the convection that occurs due to the density gradients. Okay, for example, if say there is a surface that gets heated up due to the radiation from the sun. Okay, because of the radiation from the sun. Now, since this surface gets heated up, the air molecules close to the surface of the wall, surface of this close to the ground will get heated, right? So let me denote it as red. So air molecules close to the ground will get heated up because of the ground, because the ground gets heated, and the air molecules just at a certain distance from this ground will have a comparatively lower temperature. Now, because of this difference in temperature, the density of the air will also change, and because of this change in this difference in the densities of these air molecules at different heights, there will be a certain motion of air that will try to uh, move this lighter air up and this heavier air down, right? So the heavier air will try to come down and the lighter air which is heated will try to go up. Okay, and because of this motion it will try to generate a convective heat transfer. Okay, and that's known as the natural convection. Okay, and in those cases the value of H is comparatively lower than forced convection. Okay, because in forced convection we use external sources to force the air flow or the liquid flow across or above the surface that we want to cool or heat. Okay, so that's why in those cases the rate of heat transfer will also be higher, because we are forcing the air to flow through it to take away the heat from the surface of the walls or ground. then in those cases it will have a higher heat transfer coefficient. Okay. And finally, Professor Anand discussed about radiation. So radiation is basically the transmission of energy as electromagnetic waves. Okay, in the case of radiation, we do not need any medium for heat transfer to occur. Okay, and the governing equation for the radiation is given by the Stefan-Boltzmann law, where the net rate of heat transfer is given by epsilon times sigma times A times the surface temperature to the power 4. Okay, where sigma is a Stefan-Boltzmann coefficient and epsilon is the emissivity. And again, the value of emissivity is also given. Then it is 0.92 for non-metallic surfaces, 0.6 to 0.9 for non-polished metallic surfaces, and 0.1 for polished metallic surfaces. Okay, so just the ranges are given so that if at all imagine the following type of question comes, then you will be able to match it accordingly. Okay, you just need to remember the ranges, not the exact values. So as I already mentioned, in the case of work, again both heat and work are path functions, so they cannot be represented as direct exact differentials. So they are usually represented as inexact differentials. So they are given by the symbol delta. Okay, so delta W and delta Q. And the heat transfer. So in the case of work transfer, which has a PdV work, so work transfer will be given by integral of PdV, and in the case of heat transfer, the net rate of heat transfer will be given by the integral of temperature times ds, where ds gives the net change in the entropy of the system. Okay, so about entropy we will discuss when we are dealing with the second law of thermodynamics. Okay, so then we will be very clear how to draw the TS diagrams, what does it signify, what does an isentropic process mean. So we will be dealing with that when we are considering the second law of thermodynamics. Okay, so now we discuss the first law of thermodynamics. So the first law of thermodynamics is basically the law of conservation of energy. Okay, so in the case of a cyclic process, this first law of thermodynamics takes a special form that is given by the cyclic, that gives us that the cyclic integral of delta Q would be equal to the cyclic integral of delta W. Okay, or the net heat transfer, the net cyclic integral of heat transfer would be equal to the net cyclic integral of the work transfer. Okay, in the case of a cyclic process. So here this is the derivation that was I did discuss in the very first session, that to prove why energy is a point function. So this was done very elegantly by Professor Anand to show you why the energy of the system is, or the internal energy of the system is actually a a point function. So I'll quickly go to the derivation one. So if you have any doubt, you can ask me, like you can stop me and ask me, like if you have any confusion in the steps. Okay, so okay, one more thing again, just in case if you're getting confused. So the general form of the first law of thermodynamics for thermodynamic system is given by this. Okay, sorry, where, or if for a process occurring from state 1 to state 2. Okay, and this would basically be E2 minus E1, and in differential form it will be Q is dE plus, or same as delta Q is equal to dE plus delta W. Okay, so from the from the first law of thermodynamics, for a cyclic process, we know that the cyclic integral of work is equal to cyclic integral of heat. Okay, the net heat transfer. So if we consider, say, the part 1A 2B1, basically this part 1A 2B1. Okay, if we consider this part, then from this equation we will get that the work from point 1 to 2 along part A and work 2 to 1 along part B should be equal to the net heat transfer along part A and the net heat transfer at part B. Okay, from this equation, then if we take this term to the right hand side and this term to the left hand side, then we can write Q12A minus W12A is equal to minus Q21B minus W21B. Okay, I hope this is clear. It's just simple transferring of terms from the right hand side to the left hand side and just rearranging of the terms. Okay, so this gives us equation 2. Similarly, now if we consider different parts, say part C, okay, and if we follow the path 1C2B1 to complete the cyclic process, again the cyclic integral of the net work would be equal to the cyclic integral of net heat transfer. Then we will have W12C plus W21B would be equal to Q12C plus Q21B. Okay, I hope it is clear. Okay, you can just stop me if you're not getting confused. Okay, then we do the similar manipulation as in equation number 2. Then we write Q12C minus W12C equal to minus Q21B minus W21B. This gives us equation number 3. Now if we compare equation number 2 and 3, you will see that Q12A minus W12B is equal to Q12C minus W12C. Okay, so this difference between the net heat transfer and work transfer across different parts remains constant. And from the first law of thermodynamics, for a thermodynamic process, okay, not the cycle but the thermodynamic process, we know that Q122 or change in Q, this one just denoted as Q122 is equal to change in the energy plus change in net, change in the work done. Okay, so this Q122 minus W122 is equal to actually the net change in the energy of the system, right? So this entity, that is Q minus W, remains constant across different parts. Okay, and thus it has to be a point function because it is independent of the part. So that's why it is a point function, not a state function. That's why Q12 minus W12 is the net total energy, where energy is independent of the part, and thus energy E, capital E, is a point function or a state function. Okay, so this is how you can mathematically prove why energy is a point function or a state function. Okay, then Professor Anand showed us what this term E constitutes. So this again I already discussed, so I am not going to repeat it. It's this general form of first law of thermodynamics is for a particular thermodynamic process. Okay, so thermodynamic process can just be a simple solid curve in the PV diagram, given that it is reversible. That constitutes a thermodynamic process. For that thermodynamic process, we can write the first law of thermodynamics as delta Q minus delta W is equal to dE. Okay, but for cyclic process, that if a process completes a net cycle where the initial state and the final state of the process are the same, then the first law of thermodynamics takes the form of this. Okay, it becomes much simpler. Okay, so that's the difference between the two formulas. Okay, I hope you will be able to recall it because we will be solving some problems related to it. Okay, so I will ask you to solve the problems and by implementing these laws, okay, for cyclic process as well as for a particular thermodynamic process. Now Professor Anand discussed about that the total energy of the system constitutes the kinetic energy, the potential energy, as well as the internal energy. Okay, so if there is a case where there is only the system constitutes only the kinetic energy, then the functional form of the net energy would be given by mv square by 2, where v is the average velocity of all the molecules or the system that we are considering. Okay, then in the case of where there's only potential energy, the net energy is only constitutes the potential energy, then the functional form of the equation or the energy is given by mgh, where m is the mass of the system, g is the acceleration due to gravity, and h is the height through which the object was lifted. Okay, and in the case where the system constitutes only the internal energy, basically where the net change in the kinetic energy and the potential energy are negligible, then the system primarily constitutes the internal energy. Okay, and if we apply the concept of first law of thermodynamics to such kind of systems, then we can easily find the net change in the internal energy. Okay, and in our case, in our course, we will be primarily dealing with systems that uh, which have negligible change in the potential and kinetic energy, and has primary, and the net total change in energy is primarily the change in the internal energy. Okay, by no means I'm saying that these are irrelevant. Of course they're relevant. Some kind of systems will have net change in the kinetic and potential energy as well, but for most of the systems that we'll be dealing with as a mechanical engineering students, of course this course is a general course for any student that want to take the course, but say from the perspective of mechanical engineering, if you're considering, then the net change in the energy of the system is primarily the net change in the internal energy of the system. Okay, so that's what I'm saying. That's why the internal energy becomes more relevant, but I'm not saying that the net change in the potential energy and the kinetic energy are not relevant. Okay. Similarly, again, Professor Anand introduced you with another terminology, that is enthalpy, which is again a property of the system, and where H is given by U plus PV. Okay, this term, that enthalpy, will become more relevant to you when we are dealing with flow systems. Okay, so till now we are not specifically mentioning that the system, we are not specifically dealing with flow systems, that is flow through a flow of liquid through a pipe or flow of gas through a particular channel. We are not discussing such kind of systems. Okay, but when we will discussing such kind of systems, of course the first law of thermodynamics will be as much as relevant in that case as well, but you will see that the term and the terminology of enthalpy will become quite handy when we are dealing with the flow systems. Okay, then you will be introduced with a term, with the equation named as SFEE, or the steady flow energy equation. Okay, so we'll discuss that when the time comes, but just as a brief introduction, we are introducing you with the terminology of enthalpy. Okay. Okay, so now we'll discuss one of the problems that were discussed by Professor Anand in the lectures itself, just so that uh, we can implement the concept that we have read till now. And after this problem, we will directly go to the problem that I have planned for this week's session. Okay. So a tangential force acting on the cutting tool of the lathe when turning a metallic workpiece of 80 millimeter diameter is 180 Newton. Okay, so the diameter of the workpiece is 80 millimeter, and the force that acts on this uh, workpiece is 180 Newton. Okay, so I hope most of you know what a lathe machine is. So basically what turning means in a lathe machine, so basically that it will have a cylindrical metallic piece. Mostly in most of the cases it will have a cylindrical metallic piece. Let me draw a diagram. I'm just drawing the front view. Okay, so then it will have a metallic piece, a tool, say of this form. Then what the lathe machine will basically do is it will rotate this metallic piece, and then this tool will try to chip away the surface of this I'm sorry, the surface of this metallic piece to get a perfect cylindrical shape. Okay, so it will rotate. So because of the rotation, this tool will cut through the metallic piece, and this metallic piece will chip out and then generate a perfectly cylindrical, smooth cylindrical shape. Okay, so that is what the primary one of the primary uses of lathe machines, and this is the thermodynamic system that we are considering right now. Okay, so what the question says is that the diameter of this metallic piece is 80 millimeter, and the tangential force that acts on this workpiece is 180 Newton. So it's very simple now. If you know the net tangential force and the radius of this tool piece, you will know the net torque or the net moment that acts upon this metal piece. Okay, so that's what we will. That is what exactly done in this case. So we will be doing that. But I just wanted to give you a overview of the problem that we are considering. Okay, So after 8 minutes of turning, the internal energy of the workpiece and the chip is increased by 80 kilojoules. Okay, so after 8 minutes of turning, after 8 minutes of rotating this workpiece on the lathe, the internal energy of this workpiece increases to 80 kilojoules. Okay, so it increases, so it is positive. Okay, if the frequency of revolution of the workpiece is 250 rpm, so the rotation speed, angular velocity of this workpiece is 250 rpm. Estimate the net heat transfer from the workpiece and the chips in this time. Okay, so initially our system would be the workpiece only because there are no chips generated, but after the rotation, after the turning, the final shape of the system as well as the chips will constitute our thermodynamic system. Okay, so we are mentioning it in the problem beforehand. Okay, so it is what it is being mentioned here, because it's asked the net heat transfer from the workpiece and the chips. Okay, chips are basically these metal pieces that fall off from this surface, from the outer surface of this workpiece once it is being chipped away or cut away from the metal surface due to this tool. Okay, now we have the net tangential force as 180 Newton. The radius of the workpiece would be 0.04 meter because its diameter was 80 millimeter, so the radius is 40 millimeter and r is equal to 0.04 meter. Okay, the time of rotation is 480 seconds and the net change in the internal energy is 80 kilojoules. Okay, so the rpm is given by, so it's omega, it's actually net number of rotations per minute, right? So n is 250 by 60 or 4.167 rounds per second. Now to find the net torque, we get that T is equal to F times the radius of the workpiece. So we'll get T is equal to 180 into 0.04. That basically gives us 7.2 Newton meter. Okay, so the net work done on the system, because this tool is now working on our system, on our rotating workpiece. So work is done on the system. So it is given by T to theta. Again, this formula of this work done were discussed in the previous week's session. So I'll not go in detail how we have derived it. So T is the net torque, theta is the net angular displacement. Sorry for this. Just wait for a few minutes. Sorry for the delay, just wait for a few minutes, okay? Just for, so that this sound goes away. I'm extremely sorry. There is fogging going on outside the room, so that's why the sound. Forgive the inconvenience. Kindly forgive me the inconvenience. So I hope we can continue now. Okay, so theta is the net angular displacement. So this would basically be omega t. So omega is 2 pi n. So just use that formula to get the work done from 1 to 2 is t into 2 pi n into t, where t is the time of rotation. So W1 to 2 would be 2 into 3.1416. N is 4.167 into 7.2 into 480. Okay, so once you do that, you get that the work done is equal to minus 90.4 kilojoules. Okay, why minus? Because the work is done on the system, okay, by the tool. Now from the first law of thermodynamics, we know that Q122 is equal to delta U plus W122. Okay, now in the question itself, it was given that the net change in the internal energy is 80. That is, the internal energy of the system has increased. Okay, so it is delta U is 80 and the work done from 1 to 2 was minus 90.4, right? So once you do the calculation, you get that Q1 to 2 is minus 10.4 kilojoules. So it basically tells us that the heat is being liberated from the system. That is, from heat is being generated or released from the workpiece. Okay, so workpiece is now releasing heat rather than absorbing. Okay, so that's what the minus sign basically means. Okay, so now I guess we can directly go through the questions. So you can can see the screen and tell me whether the questions are visible or not. So I hope the questions are visible. So there are 8 questions, I guess, that I have planned for this week. You can just go to the first question, and I will just go to the first question. Let me zoom out a bit so that you can look at the diagram of the slabs as well. So the question states that consider two slabs of equal length, breadth and thickness. Basically the dimensions of the slabs are the same, made of two different materials. Okay, so two different materials will tell us that it has two different thermal conductivities, K1 and K2. Okay, or more specifically kappa 1 and kappa 2. Okay, the rate of heat transfer through the slabs in the x direction is shown are the same, that is equal to q dot. Okay, the net rate of heat transfer is the same across both the slabs, that is q dot. Okay, if all the other conditions are the same and the slabs are having temperatures T1, T2, T3, T4 as shown, and T3 is greater than T1, is greater than T2, and T2 is greater than T4, choose the most appropriate option. Okay, so the options are given as K2 greater than K1, or K1 is greater than K2, or K1 is equal to K2, or none of the above. Okay, so you can either just go to the question and tell me the correct answer if you can solve it. Either you can, I would suggest you can directly use the Fourier's law of heat conduction, that is Q is equal to minus Ka delta T by delta X. Then compare the the net heat transfer rate to the two slabs. Compare the expressions and then find the relevant relationship between K1 and K2. Okay. I'll give you few minutes for solving it, and then I will go to the next question. I hope the question is clear. Okay, so did you get the answer? You can write in the chat box, comment the answer. So here we can use the Fourier's law of heat conduction. So since the net heat flux is same, so for the slab 1 we would have Q dot is equal to K1 A T2 minus T1 into x1, and for the second slab we will have K2 into a T3, sorry, the minus sign of course, T4 minus T3 next. Now since both net heat transfer rate is the same for both the slabs, so we can write K1 T2 minus T1 is equal to K2 T4 minus T3. Okay, then since the dimension of the both the slabs are exactly the same, that's why we have easily ignored or cancelled out, sorry, cancelled out a n x1, a n x2, okay, from these two relations. So now if we rearrange these terms, we can write K1 by K2 will be equal to T4 minus T3 divided by T2 minus T1. Now you can clearly see that the difference between the T4 and T3 is greatest. Okay, so this will be some negative term, this will also be some negative term, but the magnitude of this term would be greater than the denominator. So it will basically imply that K1 is greater than K2. So the correct answer will be option B. Similarly, we have the second question. So which of the following properties are desirable for a thermometric liquid in a liquid in glass thermometer? More than one option could be correct. Okay, so these are the 6 options that are given. Small coefficient of thermal expansion, large coefficient of thermal expansion, low freezing point and high boiling point, high freezing point and low boiling point. Thermal expansion of the liquid should have a linear relationship between temperature in the desired range of measurement. Thermal expansion of liquid should not have a non-linear relationship between temperature in the desired range of measurement. Okay? So these are the properties of the liquid that we use for measuring the temperature in a liquid in glass thermometer. So what are properties that you can say are desirable? Okay, so that's what the question. So more than one options can be correct. So you can write the possible options in the comment box, and then we will see and then try to match our answers. Okay. So I'll give you say two minutes to think about it. Then we can go to the next question. Okay. Any guesses? Any answers? Okay, so the correct options would be option B, large coefficient of thermal expansion, so that uh, we could easily, so that the, what to say, the readability of the temperature measurements can be improved. Like if the thermal expansion coefficient is very less, then the liquid that is being used in the thermometer will expand very less for a change in the temperature. Okay, so if the thermal expansion coefficient higher, so for a slight change in temperature, the expansion in the liquid will be comparatively larger, so that we can clearly read the distinct uh, temperature changes uh, because the temperature changes because of the change in the length of the liquid column. Okay, so basically the precision of the thermometer will improve if the coefficient of thermal expansion is large. Similarly, if it has a low freezing point and high boiling point, then the range of operation of the thermometer increases, right? So if, for example, in the case of water, the range of operation for the thermometer, like ideally, is from 0 to 100 degrees Celsius. Why? Because uh, sorry, of course, because if the liquid remains, if the boiling point is very low and the freezing point is very high, it will basically mean that the range of operation will become lesser, right? The state of the liquid will change to solid if the temperatures goes beyond the freezing point, and it will start to boil once the temperature goes above the boiling point, right? So that's why we need to increase the range of operation of these thermometers. So it is preferable if it has a very low freezing point and a high boiling point. And finally, the thermal expansion of the liquid, option E, the thermal expansion of the liquid should have a linear relationship between the temperature and the desired range of measurement. Because we saw that we had dealt with an example where the length of the liquid column was given by this relation, and it is basically a linear relation, right? It is an equation of straight line, right? So it is preferable if the thermal expansion of the liquid, basically the change in the by thermal expansion here, it will mean the change in the length of the liquid column has a linear relationship with temperature, so in the desired range of measurement, so that the calibration becomes much easier. Okay, if the relationship becomes of second order or third order, then again this calibration becomes a bit difficult, because in the case of a linear relationship there are only two constants that we need to find out, right? So since we know the freezing point and the boiling point of the liquid, uh, of uh, of the liquid that whose temperature we are going to measure, say, then we know for sure the temperature, right, at which the liquid will change its state. So the temperature is, we are certain of temperature, and once we know that, we can find the respective length of that particular liquid column in the thermometer. Okay, but if the value of the number of constants in the relationship increases, then we need to find again separate values of distinct temperature at which the water has a distinct state or behavior, or any liquid whose temperature we are going to measure has a distinct characteristic or behavior, so that we can say for certain that the temperature is equal to that particular temperature. Okay, so that's the challenge if the relationship is not linear. So the correct option is option B, C, and E. So the third question, again, I will follow a similar agenda. I'll go through the question once, give you few minutes to solve it, and once you know the answer, you can just tell me the numerical value of the solution. Okay. So thermometers A and B are calibrated at ice and steam points. Okay. These two terminologies are very important. Calibrated at ice and steam points. The relationship between the temperatures measured by A and B is given by TA is equal to, I'm really sorry, TA is equal to K plus L into TB plus M into TB square. Okay, it's a quadratic relationship. So where K, L and M are constants, and T and B are represented temperature measured by the thermometers A and B in degrees Celsius. When thermometer A reads 41 degrees Celsius, thermometer B reads 30 degrees Celsius. Okay. When B reads 41 degrees Celsius, A would read question mark. Okay. So we need to find that. So the thing is, the number of constants in the relationship are 3 in this case. So we need 3 equations to solve this, right? To find the value of the constants. So one of the values are given in this line, which is if A is 41 degrees Celsius, then B is for 30 degrees Celsius, right? So from this relationship, we can find the value of one of the constants, or we can find an equation between TA and TB, right? Now we need 2 more equations to completely solve this value of this to find the value of this constant. So where we can find it? It is given that thermometers A and B are calibrated at the ice and steam points. Okay. So if we consider the fluid to be water, then of course ice and steam points basically means water. So in that case, we will have it will give you that TA is equal to TB at 0 degrees Celsius. Similarly, TA is equal to TB at 100 degrees Celsius. Okay, so that is the relationship. I will just write it so that it becomes a bit clearer. So TA is equal to TB at 0 degrees Celsius, and TA is equal to TB at 100 degrees Celsius, and TA is equal to 41 for TB is equal to 30 degrees Celsius. So these are the three points at which you can find this equation. Then you will get 3 different equations for these 3 different temperature points, and then using that you can find the value of these 3 variables, and then tell me the answer, where what will be the reading in the thermometer B, in thermometer A, if temperature at thermometer B is 41 degrees Celsius. Okay. So I hope the question is clear. You can take your time. Say you can take 4 to 5 minutes to solve the question. I already told you the process. Get 3 quadratic equations. Solve them because there are 3 unknown constants. Find the value of the constants and then tell me the answer.
I will wait 2 more minutes and then let's see how we solved it, and then we can go to the next question. We are discussing question number 3. So thermometers A and B are calibrated at ice and steam points. The relationship between the temperatures measured by A and B is TA is equal to K plus L times TV plus M times TV square, where K, L and M are constants. And what is the temperature if the thermometer A reads 41 degrees Celsius when thermometer B reads 30 degrees Celsius? What is the temperature TA when TB is equal to 41 degrees Celsius? So here it is said that the thermometers are calibrated at the ice points and the steam point. So TA is equal to TB at 0 degrees Celsius and TA is equal to TB at 100 degrees Celsius. They are calibrated at the ice and steam points, right? So this is two relations, and third relation is given by TA is equal to 41 degrees Celsius when TB is equal to 30 degrees Celsius. So using these three relations, you will get three equations for TA and TB, using which you can solve the value of K, L and M. And once you find that, you can tell what is the value of TA when TB is equal to 41 degrees Celsius. So let us say I give you 1 more minute, since some students just joined, so you can use the calculator or anything to solve the problem. Okay, I'll wait till 7:15 and then I'll go to the next question. Okay, then I feel we can go to the solution, check the solution once, and then we can go to the next question. Okay, so we have that TA is equal to LTB, K plus LTB plus MTB square. Okay, question number 3. TA is equal to 41 degrees Celsius for TB is equal to 30 degrees Celsius. So if we substitute the value of TA and TB in this equation, we get that 41 is equal to 30L plus 900M. Okay, question number 1. Then since the thermometers are calibrated at the ice and the steam points, we'll have TA is equal to 0 when TB equal to 0. So if we substitute these values at this equation, we'll get that K is equal to 0, because it is equal to 0, this is 0, this is 0. So it will basically imply K is equal to 0. Okay, so if K equal to 0, then equation number 1 becomes 41 is equal to 30L plus 900M. Okay, similarly TA is equal to 100 degrees Celsius when TB is equal to 100 degrees Celsius. Why? Because thermometers are calibrated at the ice as well as the steam points. So TA is equal to 100L plus I'm sorry, it's not TA, it's 100 actually. So 100 is equal to 100L plus 10,000 M. Okay, So we have equation number 3. So once you solve equation number 1 and 3, you will get the value of L and M as well. Okay, so L you get as 1.52 and M you will get as minus 5.24 into 10 to the power minus 3. Okay, and K is equal to 0. We already found out from the first relation. Okay, so once you do that, you substitute the value of L and M in this equation. Sorry for going back and forth so many times. Substitute the value of L and M in this equation, and the value of TB, which is equal to 41 degrees Celsius. Right. So once you do that, you'll get that TA is equal to 53.51 degrees Celsius. Okay. So that's what we need to do. So it's 41 square. Okay, not 412. To get confused with. So let's go to the next question. Question number 4. A stationary mass of gas is compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to a final state of 0.15 meter cube to 0.105 megapascal. Okay, where pressure is remaining constant during the process. There is a transfer of 37.6 kilojoule of heat from the gas during the process. How much does the internal energy of the gas change? Okay, 37.6 kilojoule of heat from the gas. Okay, so you need to remember the sign convention accordingly. It's again very simple. You need to use this equation. Q122 is equal to delta U plus W122. So in this case, Q is already given, right? You need to find the net work done again, which is given where the pressure initial and the final states of the system are given, so you can use the appropriate PV relationship to find the net work done, net PdV work, and then once you find W122, you can subtract the work done from the net heat interaction to get the value of delta U. Okay, so let's say I will wait for 3 minutes. It's very simple. It's a constant pressure process, so work done would be given by this relation P2 minus V1. You can use this equation and then find the work done and then tell me what's the value of delta U. Okay, very simple, and Q is already given. Okay, I'll wait up to 7:21 and then go through the solution and then try the next question. Kindly try it for once and tell me the answer. It's not that difficult. It's very simple actually. Just check the sign conventions and then you can easily find the net change in internal energy. Okay. Exactly, it's really close. So thank you so much. At least you tried, and it's really close. So it is correct. Yeah, it's correct. minus 22.6, and the sign is also correct. So basically it tells us that the internal energy of the system decreases, right? So thank you so much, Shiva Kumar. I hope I'm pronouncing it correctly. Thank you so much. Okay. So yeah, so you do exactly as I mentioned. So let's go to the solution once. That we know that Q is equal, from the first law of thermodynamics, Q is equal to delta U plus W. Okay. So Q1 to 2 is U2 minus U1 plus W1 to 2. Then work done from process, say from state points 1 to 2, could be given by this relation, P is equal to V2 minus V1. Why? Because it's a constant pressure process, right? So once you do that, you will get that the net work done is minus 15.75 kilojoules. Okay. Now Q122 is already given, that is minus 37.6 kilojoule. Just substitute the value of Q122 and W122 in this relationship. So we will get that minus 37.6 is equal to U2 minus E1 minus 15.75. Sorry, minus 37.6 is equal to U2 minus E1 minus 15.75. And once you do calculate that, you will get that U2 minus E1 is equal to minus 21.85 or minus 22.6 is completely fine. Okay, so that's correct. So now let us go to the next question. This okay, I hope this will be visible. I hope the question is clearly visible. Okay. Question number 5. When a system is taken from state A from state A to state B along path ACB, 84 kilojoule of heat flows into the system. 84 kilojoule of heat flows into the system, and the system does 32 kilojoule of work. Okay, the system does 32 kilojoule of work. How much will the heat that flows into the system along path ADB be if the work done is 10.5 kilojoule? Okay. Second part is, when the system is returned from B to A along the curved path, the work done on the system is 21 kilojoule. Okay. Does this system absorb or liberate heat, and how much of the heat is absorbed or liberated? Okay, you need to find the net heat interaction. Part C is, if UA is equal to 0 and UD is equal to 42 kilojoule, find the heat absorbed in the processes AD and AB. Okay. So it's a bit lengthy question, so I will suggest that you go part by part. That is A, okay, you go to part A, then part B and part C, because these are all connected. So once you find the value of the unknowns asked in the previous question, then only you can, previous sub question of question number 5, then only you can find the next question, then you can solve the next question. So I'll suggest you go from A, B and C, okay, and then try to solve it. You can take say up to 7:30, and in fact you can just tell me the answers for A, B and C time to time. That will be much better. So you need to find for part A, you need to find WADB. Okay, you need to find WADB. Oh, sorry, QADB. I'm extremely sorry. It will be QADB. Right. Then for part B, you need to find again QBA. Okay. And finally, in question number C, you need to find QAD and QAB. Okay, it's a three-part question, so you can take your time and solve it. Meanwhile, you can give me the answers as well once you find it. Okay, try it for once. I know it's a lengthy question, but it's a good question because it's a complete implementation of all the things that we discussed today. The first law of thermodynamics, concept of cycles, then work interactions, heat interactions, everything that we have discussed till now. Okay, so try it for once, then we'll see the solution. Okay, A is minus 41.5. I will suggest that you look into the sign convention once. Approach is correct, but I'll suggest you go through the sign convention once, then you will see where you have done a mistake. So QACV is equal to, yes, 62 kilojoule. That's the correct answer. This is equal to 62 kilojoules. Okay. So QACB is 84 kilojoule. Yes, 62.5. Okay, thank you so much. It's 62.5 actually. So, okay, so since you have already found the part A, then you can go on to part B. Meanwhile, I can just discuss the solution of part A with other students as well. Okay. So QACB is 84 kilojoule and WACB, I'm sorry, I just moved the question, I'm sorry for that. And WACB is, since the system does the work, so it is positive, so it is 32 kilojoule, positive. Then QACB would be equal to UB minus UA plus WACB, which would give 84 minus 32 is equal to UB minus UA, which will give us UB minus UA is equal to 52 kilojoule. Okay. So now if you are going to a different part, then Q ADB minus W ADB is equal to UB minus UA. Now you are seeing why I am taking the state points UB minus UA, because you know that internal energy is a point function or a state function, depends on the state rather than the path followed. Okay, so you're saying that, yeah, exactly, option B is 7 minus 7. Is it minus? Exactly, right. So option B is minus, answer for B is minus 73 kilojoule. Okay, others can also try, but it's correct. Okay, thank you. So I am taking the end points UB minus A rather than the part that it has for. Okay, so it is independent of part, so I am just taking UB minus A. So it will remain constant no matter which part we have taken. Okay, so WADB is 10.5, so you get QADB is equal to UB minus A is 52 plus 10.5, so we'll get as 62.5 kilojoule. So for option B, similarly we can follow the same question, same
equations. This told that work done on the system, so WBA is minus 21 because work is done on the system, and we need to find QBA. So it is basically again UB minus UA plus WBA, right, from the first law of thermodynamics. UB minus UA is 52, right? Then, oh, sorry, we are going from B to A, right? So the final state is now UA minus UB, right? So minus 52 minus 52, and this is minus 21. Once you do it, you will get as minus 73 kilojoules. Okay, so final answer, that's a bit tricky one, option number C. You can try. Just tell me the answer. For option number C, I will suggest that you check the processes, how it is done. Check whether it's a constant pressure process or a constant volume process. Processes, by here I would mean separate processes. Is process AD a constant pressure process? Is process DB a constant volume process? What happens to the PdV work when it is a constant volume process? Use that concept, you will be able to solve it. Okay, so I'll again wait for say 3 more minutes and then see the solution. Okay, so UA is given. So because you know UB minus QA, then you can find where the value of UB. Okay, try to use that and then find the value of QAD and QAB. Okay. Now, I'm sorry. Instead of dealing with the entire cycle, deal with the processes separately. Okay. Okay. So, anyone? Okay, I will wait till 7:35 and then let's see. Okay. We have some more questions. It will be interesting if we are able to solve all of them, and then. Okay, I think that we can go to the solution once. It would be good. Okay, so let us directly go to the third part because it was a bit challenging, it seems.
So yes, sorry, we need to find QAD and QAB, right? So we have that UA is equal to 0, then and UD is equal to 42 kilojoule. Okay, it is given in the question, right? UD is 42 kilojoule. Okay, so we have that UB minus UA is equal to 52 kilojoule from the previous sub questions. Then you get that UB is equal to 52 kilojoule. Why? Because UA is equal to 0. Now WADB is equal to 10.5 kilojoule. That is also given in the that is also given in the questions. Okay, the previous questions, previous sub questions, right? Part A of the same question. Now WADB, if we go here, WADB can decompose into WAD plus WDB, right? And of course there is some work done in the process AD, but in the process DB the PDB work is equal to 0, right? So we can write that WADB is equal to WAD plus WDB, and this would be equal to 0 because it's a constant volume process. Okay, so once you apply that, you can write as WADB is equal to WAD plus WDB is equal to WAD, because WDB is equal to 0 because delta V, or the change in the volume, is 0. Then WAD is equal to 10.5 kilojoule. Then for the process AD, you can write QAD is equal to UD minus UA plus WAD. UD is 42, UA is 0, and WAD is 10.5. So QAD is equal to 52.5 kilojoule. Okay. Similarly, for now process DB, QDB is equal to UB minus UD plus WDB. Now since WDB is equal to 0, because it's a constant pressure process, if I go back again, WDB will be 0. Sorry, WDB would be equal to 0 because delta V equal to 0 in this case. Okay, so we can write, let me go back again. So we can write QDB is equal to UB minus UD plus WDB, and WDB is equal to 0. So QDB is equal to UB minus UD, where UB is 52, which is we already found out here, and UD is 42, which is given in the question. So we can write QDB is equal to 52 minus 42 is equal to 10 kilojoule, which is the answer. Okay, so is it clear? Okay, thank you. So let us go to the next question. Yes. A stationary fluid system goes through a cycle shown in the figure given below, comprising of the following processes. Process 1 to 2 is the isochoric heat addition process, okay, of which has a heat addition of 235 kilojoule per kg. Okay. Process 2 to 3 is an adiabatic expansion to its original pressure with the loss of 70 kilojoule per kg of internal energy. Okay, adiabatic expansion. So by adiabatic, if you are not clear by now, adiabatic process will basically mean a process which does not have any heat interaction. Okay, so any heat interaction in this process will be equal to 0. Basically Q2 to 3 will be equal to 0. Okay, and it has a loss of 70 kilojoule per kg of internal energy. Okay, check the units as well. Okay, process 3 to 1 is a isobaric compression to its original volume with heat rejection of 200 kilojoule per kg. Okay, prepare a balance sheet of energy quantities and find the overall changes during the cycle. So you need to find basically say for 1 to 2 you need to find the net work interaction and internal energy. Again, everything that is not given. So for 2 to 3 you are not given the net work interaction. To find you have to find net work interaction, and for process 3 to 1 you need to find the net work interaction and internal energy change. Okay, so basically what we are trying to generate is, say if you have a table such as process delta U, Q and W. So process 1 to 2, 2 to 3 and 3 to 1. So for first process isochoric heat addition, so it is 235, it will be positive, right? Q is positive, so it is 235. I hope my writing is clear enough, otherwise again you might get confused. W and delta U do not know. For 2 to 3 adiabatic expansion, original pressure with a loss of 70, so it is minus 70, right? It's loss of internal energy. This is 0. Okay, again isochronic heat addition, so work done will also be 0. You need to find delta U. So this is question mark, this is question mark. For process 3 to 1 isobaric compression to its original volume with the heat rejection of 200 kilojoules, so it is minus 200. So now both are question mark, so you need to find both of them. Okay, so yeah, try to solve it. Actually what I can do is, since this is a very, like, you cannot explicitly say the answers, so what I can do is, I will give you 4 minutes, say up to 7:45. You can try to solve it. Again, it's a simple use of the first law of thermodynamics, that is Q A to B is equal to UB minus UA plus WA to B. Okay, just use this equation for all these distinct processes, then find the unknown values. I know it will be very simple, and then we can compare our answers. Okay, I'll wait for up till 7:45 or 7:46, and then we can compare our solutions. Okay, I hope it sounds good. Then we will see a very interesting thing. Okay, of course related to the course only. So yeah. Okay. Okay. Interesting. Okay, let me check it. So U2 minus U1 is 235, you're saying. Okay. Then W31 is minus 35, right? And W23 is 70 kilojoule per kg. And energy interaction from 3 to 1 is minus 165. So, okay. Excellent. Like, thank you for the answers. All are all are exactly correct. So now what I will suggest you to do is, you can now clearly see that this diagram that we have in our hand, in the PV diagram, it is constituting a cycle, right? A thermodynamic cycle. So why don't you try to find the sum of net heat interaction and work interaction and tell me, are they equal or not? Okay. What I'm trying to say you is, just find Q1 to 2 plus Q2 to 3 plus Q3 to 1, and then W1 to 2 plus W2 to 3 and W3 to 1, and just tell me whether they are equal or not. Just check it, because all of an entire table is completely filled now, so it should be a simple task, right? So let me just see your answers and fill the table. So it is okay, great. The work done 3 to 1 is minus 35, is minus 165, is 70, and 235. Okay, so you're saying that, oh, minus, is it minus? Okay. Okay then, so you're saying it is plus 35 in both the cases, so you're basically saying summation of all Q and summation of all W for the cycle is equal, right? So doesn't it basically give us the first law of thermodynamics that we discussed for a cyclic process, right? This is what something that interesting that I wanted to show you. Like, once you solve the value of the internal energy, the heat interaction and the work interaction for cyclic process, you'll see that once you sum up all the work interaction and heat interactions, they should be equal to each other, right? And this is how you will say, or this is how you will find that your calculations are in fact correct. In fact, there are sometimes many questions asked in the examinations related to this concept itself. Like, you will be asked to fill the table, and the examiner will try to check whether you know that concept or not. Like, whether you do not, whether you know the concept or not, of that the net sum of net heat interaction and work interaction would be equal to 0, right? So yeah, of course. Why? Because it's a complete cycle, and then the, yeah, it's actually the sum of heat and work, so that's fine. Yeah, of course this has to be, right? Since the endpoint of the processes are same, then the net change in the internal energy would be 0, right? Okay. Okay, then thank you for this active participation. Now let us go through the final set of questions, and then we can end today's session. Okay. Okay, question number 7 is again an interesting one. So let's try to solve it. Okay. A fluid confined in a cylinder by a spring-loaded frictionless piston, so that the pressure in the fluid is a linear function of the volume. P is equal to A BV. Okay. P is equal to A plus BV. Okay. And the internal energy of the fluid is given by the following equation. It is U is equal to 34 plus 3.15 PV. Okay. Where U is in kilojoules. Check the units always. Okay. U is in kilojoules, P is in kilopascal, and V is in meter cube. If the fluid changes from an initial state of 170 kilopascal to 170 kilopascal 0.03 meter cube to a final state of 400 kilopascal and 0.06 meter cube, with no work other than that done on the piston, find the direction and the magnitude of work and heat transfer. Okay. So you need to find both the work and heat interactions, okay, in this question. So they are saying there's only PD work involved. So, and the relationship between the pressure and the volume is also given. So we need to find the net heat and work interactions, okay. So the relationship between for U is given, so you can find U2 minus U1, because U2 would be, then it will basically be 3.15 P2 V2 minus P1 V1, right, because this constant will get cancelled out. So from this you can find U2 minus U1, and work you can find using this relation. You can first have to find work would be integral of PdV, right. Now the important thing to note here is that you do not know that the pressure remains constant, and of course it changes as you see the initial and the final stage, the pressure changes, right. And you are given a relationship for pressure in terms of volume. So what you can do is make this integral in terms of a single variable. So you can indeed write it as a plus bv, because p is a plus bv into dv, right. So what you need to do is you need to find the value of a and b first to evaluate this integral, okay. And how you can evaluate a and b, a and b? So you have that p is equal to a plus b, so it will give us 170 kilopascal is equal to a plus b into 0.03, right. Similarly, the final set is 400 kilopascal is equal to a plus b into 0.06. You can solve these two equations to get the value of a and b, then evaluate the integral to find w1 to 2. Then since you have w1 to 2 and u2 to 1, find the value of q, okay. Pretty simple steps, but you need to know what to do after another, okay. So it's quite simple, but you can just try and tell me the answer, okay. Solve the equation for the pressure and volume relation to find the value of a and b. Then you can evaluate the integral and then find the network interaction. It will be quite a bit lengthy, comparatively lengthier calculations. Of course, similar calculation we have already done in the previous questions as well, but this will again also be lengthy. Take your time and do that, and then just tell me the answer. Okay, so I see one answer. A is 400. Let me check. Okay, A, no, A is not 400. So you can just check the calculation again. So you need to see. Okay. Okay, let me wait till 7. Okay, let us keep it as a last question for today. Let me wait for a few minutes more. And you can try. Okay. Then I'll even tell you how to solve the last question. It can be an exercise for you because we solved similar question to the session. So then it can be an exercise for you. Okay. So I think for the sake of saving time, I can go through the solution once. Extremely sorry if you all were trying and I am just rushing it, but for the sake of the time for the session, I will go through the solution once. Then you can cross verify with your solutions. Okay. Extremely sorry for that. Okay. So the change in the internal energy of the fluid during the process is given by U2 minus U1. So we have that U is equal to 34 plus 3.15 into PV, right? So U2 minus U1 will be given by 3.15 into P2 minus V2 minus P1 minus V1. Once you do that, you find that U2 minus U1 is equal to 59.5 kilojoules. Okay. So the sign convention directly tells you that the internal energy of the system increases. Okay. Now we have that P is equal to A plus BV. Okay, so we have that the initial state was 170 kilopascal and 0.03 meter cube. Okay, similarly we have 400 kilopascal the final state and final volume is 0.06 meter cube. Once you substitute, once you solve this equation, both of these equations, you will find that A is equal to minus 60 kilonewton per meter square and B is 7667 kilonewton per meter to the power 5. Okay. Once you substitute the value of A and B in this equation, in this relation, we have work done is equal to V2 to V1 to V2 of integral of P dV. So P is A plus BV. If you do the integration, we will get that it is AV plus BV square by 2 from V1 to V2. If you substitute the value of V1 and V2 in this equation, we'll get that W1 is A V2 minus V1 plus B V2 square minus V1 square by 2. Just substitute the value of A, B and V2 and V1, we'll get that W1 is 8.55 kilojoules. Okay. So since now we have both internal energy change and the work interaction, we'll get that Q1 is 59.5 plus 8.55 is equal to 68.05 kilojoules. Okay. Sorry for rushing the solution, but I hope it was clear. It's just the matter of finding the value of the constants A and B. Okay. Is it fine? Okay. Thank you. So let us just go to the last question once. I'm sorry that I'm exceeding the today's time limit. So the last question is, an engineer proposed a new temperature scale in which the ice point of water is taken as 200 degree Q and the steam point is taken to be 500 degree Q. Okay, I don't know how to say it. Just the different unit of temperature that the engineer has proposed. Okay, where the ice point of the water is now 200 degree Q and steam point is 500 degree Q. What are the corresponding values in degrees Celsius for 100 degree Q and 300 degree Q? Okay, if the relationship between the two temperature scales is linear. Okay, let me just directly go to the solution so that you can save time and just go and get you can also understand it. Okay, so it is given that the T, let me denote the temperature at the new temperature scale. Yeah, of course, yeah, we can use that. So no, actually we need to correlate the temperatures rather than the lengths. Okay, because we are relating the temperature at two different thermometers, two different temperature scales that is devised by the engineer. Okay, so rather than AL we can use AT or A plus BT. Okay, so let me denote T dash as the temperature in the new temperature scale that is devised by the engineer. Okay, so T dash ice is equal to 200 degree Q and T dash steam is equal to 500 degree Q. Okay, now T ice is and the normal T is the temperature in the normal thermometer, normal temperature scale. Okay, so T ice is 0 degrees Celsius and T steam is 100 degrees Celsius for water, right? Okay, so now the temperatures are related in actually sorry, it should be scales. Okay, so it is they have a the two temperatures have a linear relation between them. Okay, so let me write T is equal to A plus B T dash, where T dash is the new temperature scale that is devised by the engineer. Okay, so I have that 0 is equal to A plus B into 200, because T dash ice is equal to 200, right? So 0 is equal to A plus B into 200, and 100 is equal to A plus B into 500. So once you do that, you get that 300B is equal to 100, and B is equal to 1 by 3, and A is equal to minus 200 by 3. Okay, once you use the relationship, once you use the value of this A and B in this relationship, you get that for T dash is equal to 100 degree Q, you get T is equal to minus 200 by 3, which is the value of A, plus B is 1 by 3, so 1 by 3 into 100 is 100 by 3, so T is equal to minus 100 by 3, or minus 33.33 degrees Celsius. Okay, similarly, if T is equal to 300 degree Q, T would be minus 200 by 3, this is the value of A, and B is again 1 by 3, the 1 by 3 into 300, so it is 300 by 3. Once you do the calculation, you get that T is equal to 100 by 3, or 33.33 degrees Celsius. Okay, is it clear? Because see, we were mentioning a right relationship, but it was for the relationship between temperature and the length of the liquid column. Okay, but in this question they have suggested that the temperature scales very linearly. Okay, so there has to be a relationship between the temperature scales. So that's why I have used the linear relationship between T and T dash. You can also use T dash is equal to A plus BT. Then you will get the defined value of A and B. Use that and find the value of T accordingly. Okay, is it clear? Okay. Okay. Thank you so much. Then let's end today's session here. Then we'll meet next week. Okay. Thank you so much for attending today's session and being so interactive. It was very helpful and interesting. Okay then. Thank you so much. Let's meet next week.